we have seen Fourier expansion, the properties of Fourier expansion. Yesterday, we saw one way in which it can be used, which was in the field of property testing. It gave us this, in some sense, a surprising result. That we can check linearity of a function with only constant number of queries. There were some promises and things involved, but still, we only had to query very few times and we could still test whether a function was linear or not. Today, we move on to a different application, a different domain. This is called error correcting codes. How many people are familiar with error correcting codes? Probably a show of hand would be helpful. Okay. Okay, so I see 3. Okay. Okay, fine. So since many of you have seen error correcting codes, let me ask you first what you understand of error correcting codes. Let's say, Udit, you want to start?
Error correcting codes are basically protocols in which we should send the data so that if during transmission any error occurs in the data, then we can correct it at the other end.
Okay, good. And what Udit said is kind of clear from the name also, right? The fundamental problem is transmission of data between two parties, Alice and Bob. There is some message or there is some data which Alice wants to transfer to Bob. Some we like Boolean domain, so let's say it is some string in -1, 1 to the power k. We can always assume without loss of generality that our message is encoded in this -1, 1 format. Alice wants to transfer M to Bob, but the problem is that the channel given to them, this channel is noisy. What does that mean? It means that the message can, or any bit of the message can change because of the presence of noise. Does this model seem familiar? Have you seen it somewhere else? Okay, I will argue that this is in sense close to cryptography, where also our task was to pass message between the two parties. And you have seen cryptography, we did it as an application in the first class, but definitely I've heard of cryptography and you know what it is. They look similar, but they are very, very different. One of you would care to tell me why these two are very different?
Basically, I mean, in coding theory or in error correcting codes, the adversary happens to be the surrounding noise, or it's unintentional in many aspects. while
Very-
in cryptography, there's an adversary who wants to crack the message.
Very nice. Very good. That's a perfect answer. In case of cryptography, we had an adversary in the sense that it was an intelligent adversary. In case of error correcting code, I would say there is no adversary. Our adversary is noise, which is random. It will randomly affect our message. And we don't need to hide our message from anyone. In case of cryptography, we wanted to make sure that the message should not be captured by you. In this case, there is a noise which is going to change the message, but we still want to make sure that the message is captured by Bob. Still, even though there might be some changes, still the message is captured. The simple model, which is studied most of the time, is that every bit can change with probability. Okay, think of P as some small thing, like let's say 0.1 or 0.01 or something like that. There's a small probability that every bit can get flipped. Trivial question is it possible to transfer the message without any error, such that Bob can always correct the error? Yes, no?
What was the question exactly? Once again?
I'm asking, is it possible that you can devise a protocol such that you can always correct? With probability 1, Bob will be able to correct the error. Can that happen?
No, I guess.
Very good.
I'm
Yeah,
feeling it's impossible, but I don't know why.
right.
I mean,
right?
Shannon's theories, they exist. I mean,
Arey, you don't have to go to Shannon, man. Let him be in the grave. Enjoy his time. It's it's not that. It's simply think about this simply, right? Since there is a non-zero probability of every bit being changed, right? If you want to transfer two messages, one message can get transferred into another message with some non-zero probability, right? And then Bob has no way to figure out whether error happened or it did not happen. Do you see that?
yeah.
Right? So you cannot succeed with probability 1. You cannot, because if you have one message, then there is nothing to do. But if there are two messages, it might happen that M1 gets transferred to M2. There is a non-zero probability of that. And if M1 gets transferred to M2, Bob has no way of knowing whether M1 was sent and changed to M2 or M2 was actually sent. Right? In other words, like before, like in the case of property testing, Bob should succeed with high probability. This is intuitively clear. I just wanted to spell it out. Any doubts about this? Our goal of succeeding, always succeeding, is impossible. That's why we will make a realistic goal, which is that Bob should succeed with high probability. Sounds good? Now we will change the model slightly. We will say that instead of saying that every bit can change with probability P, we will say that few bits of the message can get changed. It's not possible that the entire message gets changed. Only few bits of message can get changed. Since P is less than 0.1 or something, we know that, with very, very high probability, only few bits of the message can get changed. Whenever many bits get changed, we won't worry about it. That will anyway be an error. But that error probability is small.
By few, do you mean at most a constant fraction of k, or at most a constant number of bits?
That depends. I haven't defined the model completely yet, but it depends on many things: the length of the message, the number of the code words, and all that. But it will be some multiple. It will be some constant fraction of the length of the message in some sense. But it can depend, right? But there is some connection there, right? Don't even worry about. Think about sending 10 length 10 messages. Our message or codes are element of -1 to the power 10, then we will say that, okay, not more than 3 bits can change. Okay.
Okay.
And but think of it as constant tau. Once we say the model, then asymptotics will be good. Now, in this model, in this new model where very few bits get changed, we want to succeed perfectly. Sounds good? Our error model now is slightly changed, but that doesn't matter because there is a very, very small probability that a large number of bits will get changed, and then we won't care. Then we will say that our protocol anyway ended up in there. Since we're allowed to err on with some probability, whenever we have more than some bits of errors, then we will say fine, we don't care. Right? So that's so then our model is changed. Very few bits get changed, and we want to succeed perfectly whenever very few bits get changed. Now, knowing this, can you think of an easy way to transfer your message? Suppose let's simply put that you only wanted to transfer -1 or 1, a length 1 message. How can you transfer it to Bob when you know that very few bits get changed and still get the correct answer? The first error correcting code. I want you to design the first error correcting code. I will wait. I have enough time. So please think. Let me make it precise that you know that not more than 1 bit can get changed. In the transmission, at most 1 bit can get changed.
So we can transmit 3 bits of same bit. So if the message is -1, we will transmit -1, -1, -1. So when Bob receives, the actual message will be the majority bit.
Very nice. This is very, very natural, right? This is called the repetition. What do we do? If we want to transfer -1, instead of sending -1, we will send -1, -1, -1. If we want to send 1, then we will send 1, 1. We know that at most 1 bit will get changed. Bob will just take the majority and know what we wanted to transfer. Sounds good? Any questions about this? This explains the model clear, right? The problem is that this code is not very efficient. I'm not going to say how. I will just define the formal framework of repetition, formal framework of error correcting codes, and then it will be clear to you that this is not that efficient. And the task or the objective is to find better codes. Let me go ahead and tell you what do I mean by an error correcting code. Let me just define it formally, and then we can start looking for better codes. Suppose Alice can transfer n bits to Bob, then the Alice's thing which she transfers will actually be an element of -1, suppose she wants to transfer k messages. In that case, she will encode M1 as C1, M2 as C2, MK as CK, where C1 to CK will be element of, they will be element of
-1, to the power.
right. These are called the code words. Now, any subset of -1 to the power 1 is actually called a code. If you think about it for some time, this mapping or this mapping can actually be stored by Alice and Bob. In other words, how do I name M1 to MK are not really. How do I map my message to codes is not that important. That's just a labeling, right? That mapping can Alice and Bob can store in their own respective files. For the transmission, for our problem, we can just worry about the codes. And we want to, in some sense, do two things. Have many code words, that way we can transfer many different messages and have the ability to correct errors. These are the two things we have to keep in mind, and they will obviously interfere. That is where a trade-off kind of thing will happen. But generally, when we talk about error correcting codes, this is what we want to do. Just a reminder that I have taken my alphabet to be -1. Generally, when people talk about error correcting code, they will say that the message or the code is a subset of sigma to the power n, where sigma is some alpha. We will take the simplest case and we will take sigma as -1. Right? For our example, RC was a subset of -1 to the power 3, and it was exactly how many code words did C have in the repetition code?
2.
Yes. These were the two code words, and C was a subset of -1. You can extend it, and it could correct errors up to 1. If we knew that less than 1 bit, less than equal to 1 bit has changed, then we can recover our original code. Bob can figure out whether 111 was sent or -1, -1, -1. With this, now we have the formal meaning of what we call an error correcting code. The question is, when is code good? When can it correct errors on, let's say, many bits? See, we know that small number of bits can get changed, but we want to make sure that a good error correcting code is something which can correct error on this. When I say small number of bits, we want to in some sense say that the small is not so small. I can correct errors up to 3 bits. I can correct errors up to 5 bits. I can correct error up to 7 bits. So when you can correct error on more bits, your error correcting code is strong, or it is better. And this can be formalized using the notion of Hamming distance. Do you remember Hamming distance? What is the Hamming distance between two strings x and -y, x and y?
Number of minus ones in the product of x and y,
Okay, right. Number of places where x and y,
where they differ.
right. Because even if you take it to be from 0, 1 domain, this is the definition of Hamming distance, right? So I would like to be general definition. And now I can define the distance between two code words. What should be the distance between two code words?
Hamming distance.
Hamming distance.
Right, because that's the thing I introduced just now, right? What else could be? But then more importantly, what will be the distance of the code?
The minimum of the Hamming distance on all the pairs.
Correct. Minimum over ci, cj element of C. Right? This agrees with most of the notions in complexity where we define distance or a measure by worst case measure. Right? Now, why am I calling it worst case? If the distance between C1 and C2 is more, is it good or is it bad?
Good.
Right? Clearly, if the distance between C1 and C2, if the Hamming distance between C1 and C2 is more, it is much harder to convert C1 into C2 or go close to C.
So
Mhm.
we should also add CI not equal to CJ.
Oh yeah, obviously. It is very, very important. That's why I will add it in red. CI is not equal to CJ, right? So better to have large distance. That means worst case distance between two code words. That's what I'm going to define as the distance between distance of the code. Once I define the distance of the code, again, I can talk about two notions. When can I detect error? How many bits of error can happen at which I can say that, okay, there is some error. Then Bob can figure out, oh, some error has happened on the transmission. Let's say we are going to transmit.
Less than the distance of the code.
Right. Let's say we are going to transmit our messages using some code C, and D is the distance of the code, then it is not difficult to see that if less than d bits get changed, then Bob would detect error. Bob would know that error. He might not be able to say which code word was sent to him, but he can definitely say which that something happened in my message. We can retransmit the message or something. But more importantly, we are interested in correcting it. When Bob can say that what message was actually transmitted to us. So let's say we are again transmitting in terms of C, where we know that D is the distance of the code. How many errors can we allow such that if the errors are less than that threshold, then Bob can recover what message was sent? Is the question clear, or was it too long a question?
Can you repeat the question?
So it was too long a question, right? So I'm asking, how many errors can we tolerate? That means if the number of errors are less than this threshold, then Bob can figure out what message was sent in terms of obviously distance.
D by 2.
Very good. This is something which I won't prove. This is something where you think about it for some time and you will realize that this is correct. What is the theorem? If number of errors are less than d by 2, then Bob can correct error, or in other words, recover the original code. Makes sense? Basically, the point is your code word is C1 and C2. If the errors are less than d by 2, then whatever message Bob will get, he knows that there is only a unique code word which is at most d by 2 away from n. There cannot be two code words which are less than d by 2 away from. What is this called?
Triangle inequality.
Triangle inequality is
Good. What we learned is that the notion of detecting error and correcting error depends on this distance C. We want to have codes with large distance. The only problem is, you think of a problem, then the repetition codes are the best, right? They have the best possible distance.
The number of messages that we can send would get smaller.
Very good. Yes. Again, there are two things. You want to maximize number of code words sent and we also want to maximize the distance. If you think about this for a bit, you will see that these two targets contradict each other. If you try to maximize distance, then the number of code words you send will reduce. If you try to maximize number of code words, then the distance will reduce. So this is a trade-off. And then you search for better and better codes. One of the codes which are good in this way and have been used for transferring messages is called Hadamard codes. How many people have heard of Hadamard codes? Please raise your hands. Okay, good. Then we are learning something completely new.
Sir, can we say that in this case, the optimal solution that would be somewhat that the code words must be uniformly distributed in the -1, 1 to the power n thing like distance.
The problem with that is you don't want a probabilistic arrangement on your code words. No? Finally, when Alice and Bob sit down and decide how they will send things, they cannot be deciding on the base of probability. You are right.
No,
that
I mean symmetrically in some sense.
yes. If you had a continuous space, it might have been easier to convert this symmetrization intuition into code. But
Yes.
-1, 1 to the power n is a discrete domain, right?
Yes, sir.
And then to say that you in every direction you want to have one code word or something, that would actually be pretty bad. It is not easy to formalize, and that's why there is the entire field which is devoted to finding better and better codes. Your intuition is correct. It makes much more sense if the domain was continuous. The base domain was continuous. Sounds good? Udit, did I
Yes.
answer your question?
Yes, sir. Yes.
Okay. Let's talk about another nice codes, figure out their distance. And we know that it is very, very useful. So let's figure it. Let's get to know another array. What is Hadamard code? Actually, your codes, let's define n to be 2 to the power n for some small n. Then my code word is a subset of -1, 1 to the power n. Each of my code word, the elements of this code C, they will be indexed by a subset S. Notice there are two n's here, small n and capital N. Capital N is the number of subsets of size small. You have a code word for every subset of size. How many code words do you have? How many code words do you have?
2 to the power 2 to the power n.
Yes. There are 2 to the power n code words. And what is this code? This code is the truth table of our friend pen. Or I should say the last column. In other words, fix an ordering on all inputs. There are 2 to the power n inputs. Let's say the ordering is x1, x2, up to x capital N. Then CS is chi-s of x1 concatenated with chi-s of x2 chi s of,
Sir, shouldn't there be a total of 2 to the power capital N code words?
sorry,
And
Shouldn't there be a total of 2 to the power capital N code words? Not
and so
capital
C,
N code
C
words.
should be a subset of -1, 1 to the power small n.
no.
Capital.
That is why I'm saying you have to be very, very careful now. I have just defined the code word, right? That is when you will see that it is actually a subset of -1, 1 to the power complete N, capital N. So let me answer first question first. First, someone asked, why are there not 2 to the power capital N? How many subsets are there of size small n? How many such subsets are there? 2 to the power n. And each of this subset corresponds to one code. That means I have only these many codes.
So isn't it possible that the in total there can be 2 to the power capital N strings of length capital N, right?
That is correct. The length of this is 2 to the power n. But obviously, if you
Yeah.
take every string there, then you will have 0 distance or 1 distance.
Okay, so we are taking small n, we are taking capital N strings out of this set.
We
Okay,
are
so
taking,
the-
yes. Yes. I am taking capital N code words out of 2 to the power n possible strings.
Code word strings, right?
And here you can see that the length is capital N, right? Because chi s of xn will be 1 bit. Should we do a small example? Let's take an example that will clarify it clearly. Let's take n to be 2. Then my subset s will be a subset of 1, 2. Let's take s to be 1. Now I want an ordering on my inputs. How many inputs are there? How many x's are there of this kind? 4, right? Let's arrange them. That means C of 1. What will this be equal to? What will be this code word?
-1 1.
Sorry,
Actually, I missed the part with the chi-s in the previous page. Can you show that
sure.
for once?
If this is confusing to you, let me just, okay, I understand why there might be a confusion. These are not bits of the input, right? These are different inputs. Let me denote them by this. Does that make sense? I have capital N inputs, right? I'm arranging them in order. So each of these are element of -1 to the power n. Each xi is an element of -1, 1 to the power n. And now this will be chi s x1, chi s x2. I think this is a better notation. Otherwise, you get confused with. Did this help? These are different inputs. Does this make it clear?
So what do you mean by input here?
Input, I'm thinking of inputs as this for our different for our functions, right? I was talking about truth table of chi-s. I'm thinking of chi-s as a function. If I think of chi-s as a function, what are the inputs? The inputs are all strings of length small.
Okay.
Right? Let's look at an example. This will make it clear, right? If n is equal to 2, my subset S is 1, 2, then all my inputs are this, right? My chi-s of x is just x, where my function chi-s is actually, I'm thinking of them as functions on n bits. This is x subscript 1. This is the ordering on all possible inputs.
Then this C1 should be x1 at 1, 1 and x1 at minus 1, 1, right? x1 at 1, minus 1, x1 at 1, minus 1, minus 1.
The C1, which
Yes.
yeah, it will be chi-s on all the inputs, right?
So chi set 1 on all the inputs. Right?
Yes, yes. S is this. I'm just writing S, but it always means it's this one. It's x1. That means 1, minus 1, 1, minus 1. This is an element of minus 1 to the power 2. This is my code.
So we can say that my code words are the basically last columns of all the truth tables of all my chi-ss.
Yes.
I mean, they are chi-s evaluated on all the total power and inputs for all ss. So these are just the CSS.
Yes. Yes. Right?
Yes, sir.
Okay. Any questions about what is Hadamard code? Are we good? Can we start looking at its properties? Should we do another example? Raise your hand if you want me to do another example. Okay. Let's take S to be 1, 2. Tell me what is CS. Now my F, think of F as x1, x2. Then I want to evaluate F on 1, 1, F on minus 1, 1, F on 1, minus 1, F on minus
1 minus 1 minus 1.
1, minus 1, minus 1. This is my code. Okay. Now, knowing this, what is the obvious question? Now, once we know a code, what is the question? What is the obvious question?
What is the distance of the code?
Good. What is the distance of Hadamard code? Sorry, Hadamard code. Let's say capital N. It's the length is capital N. Any guesses? Is it capital N? It cannot be, right?
Here, the length of the actual messages MI does not matter, right? Because we are
Uh,
mapping them to CI.
Yes, forget about MI. MI is gone. Yes, if you want to be to go into the detail, actually the length of the MI should be log of number of messages, right?
Yes.
That's the easiest way to kind of encode all these messages. But we are not worried about that. Let's just try to maximize the number of codes.
Okay.
So when I say capital N, that's the length of the code words. Don't worry about the length of the message. That's not relevant. Any guesses? Is it N? Is it capital N? That you know, right?
It's obviously not capital N because then
Yes.
it's been that every bit in every two messages, every other bit different.
Exactly. Exactly. Okay. Let me ask different question. What is the distance of code words CS and CT? This is equal to number of.
I mean, this would be something like to summation chi evaluated over S symmetric difference with T.
Good. Let's go step by step. You are going in the right direction. The distance between these code words by definition is number of x's where what happens? Can you write it in terms of chi s and chi t? Number of x's where?
Chi S is not equal to chi T.
Everyone is fine with this? Yes, no. If you're fine with this, say yes.
Yes.
Yes, fine.
Yes, sir.
Oh, is there anyone who is not fine with this? Okay. The distance between CS and CT is number of x's where. But what is this quantity? How can you calculate this quantity? We did something like this yesterday also.
I mean, if they are unequal, then their product is going to be -1.
Minus one.
Otherwise, it is going to be 1.
Correct. Okay. What is this quantity? Remember, we have always talked about this inner product.
This is basically the number of places
This
where they're
equals
equal
number.
minus the number of places where they're unequal divided by 2 to the power n.
Right? And what do I know about this?
This equals 0.
Delta ST. I mean,
Yes.
the
Yeah, assume S is not equal to P, right? Because we are only in the distance between CS and CS is 0, right? So we won't worry about that. But this is 0. What does it imply? Number of x's where chi sx is not equal to chi st is equal to
The number of places where they're equal.
which is what does that mean in terms of capital N?
Capital N
N by 2,
N by
I mean,
2
distances.
places.
Yes, because either they will be equal or they will not be equal.
Mhm.
Correct. If they are equal at the number of places where they are equal is same as number of places where they are not equal, then both conditions happen at n by 2 positions. Right? It turns out that the distance of, and since this is true for any two code words, even the distance of the code is also n.
N by 2.
This is a very nice property of Hadamard codes. Its distance is n by 2. Not just that, if you look at any pair of code words, the distance. That was not needed to define distance of C, but it has a stronger property than just saying that distance of C is n by 2. Every pair of code words have the distance n. This means we can correct errors up to how many bits?
N by 4 bits.
Up to n.
In a way, n by 4 minus 1.
So n by 4 minus 1. Yeah, yeah. See, this plus minus 1, you don't have to worry about when
Yeah,
we're
yeah.
talking about capital N, right? N by 4. But
Yeah,
yeah, you are right. N by 4 minus 1. It depends whether n by 2 is even or things like that, right? So, yeah.
Yes,
Oh,
yes.
actually, it is always even to the power. Sorry, yeah. You are right. And anyway, those are trivial technical issues. We won't worry about that. Good. So the distance, if the distance is less than n by 4, then we can correct. But how will you correct this? You also need some way, right? If you go over all possible code words and see with what code word is closest, it will take a lot of time. Find the see Alice Bob. Alice decided that she wants to send the code word CS, but with transmission, some W will. Now, what is the problem? We know that Hamming distance between W and CS is less than how much is it? How much is it?
N by 4.
N by
N by
4.
4.
How do we recover W?
So if the number of error bits, like number of bits which have changed, is more than n by 4, then it will be like the passed message or the received message by Bob will be closer to some other code word. So some other wrong code word.
Correct. Correct. Then
Okay.
we don't know which one it is close to, and we can't recover the code.
Okay, so we are assuming that the number of error bits will be less than n by 4.
Yes, yes.
So we have
Given
to
this-
recover CS actually.
Sorry,
We will be recovering CS, no?
we have to recover CS. Is that what you are saying?
Yes. Sir.
How will we do it? That's the question.
Yeah. I'm saying that maybe we
Yeah.
have to recover W.
Okay. Oh, sorry. Yeah. This typo you also. Yes. Question is how?
Just a small thing. Just a small thing. If once we actually do recover CS, we also need to convert it back to the way original message, right? So
Arre,
are we
Papa,
guaranteed that? I mean, yeah, we know that we don't care about that.
that
for
table is
correction
present
itself.
with Alice and Bob, right? That is just a lookup in the table,
Okay.
right? So they can always look up in the table.
The correct code word would be the one for which the coefficient in the Fourier transform would be the highest one in this one.
Exactly. This is something which I want you to understand, right? W hat S. This is something which we did used yesterday also, and we're going to use it today also multiple times. What do we know about W? W is a string in -1 to the 1 to the power capital N. That's why I can think of W as a truth table of a function also. I will denote them by the same name so that, yeah. Right? Do you agree that any string of size capital N of -1, 1 can be thought of as a function from -1,
Yes.
1 to the power N to -1,
Yes.
right? And then W hat S is basically a measure of distance between
Highest
W
and W.
and S. Very good. In other words, if we know that W minus CS is less than n by 4, what can I say about W hat S?
Uh, it will be more than 1 minus n by 4 divided by 2 to the power. I mean, 1 minus 1 by 4.
No, almost correct.
Excuse me, sir. How did we say that W hat S is a measure of distance between W and phi?
You are going to see just now. You will see in 2 minutes.
I mean,
What-
sir, like yesterday, how we did that if f was equals to chi, I mean, when we
Yes,
tried
1 minus
to
1 by
find the
2
middle.
it should be. It should be 1 by 2.
exactly. Because what is W hat S? It is 1 by 2 to the power n number of places where W and chi S agree, minus number of places where they disagree. Right? This inner product we have seen so many times now,
Yeah, yeah.
right? And now
Yeah,
we
so
know
it is a measure of distance.
that this is more than 3n by 4. They agree at least 3n by 4 places. And they disagree at most n by 4 places. Sorry, this should be 2 to the power.
1 by n.
So this is greater than half. Sounds good? And now this important point is clear. If W and Chi-S are very close, then W hat S will be very. If they are the same, then W hat S is 1. If they are very close, then W hat S is equal to 1. If they are completely different, then W hat S is minus 1. If the distance between them is half of the length, then W hat S is. Other way to say it is, as W minus CS varies from 0 to n, W hat S varies from 1 to minus 1. W minus CS is equal to n by 2, then W hat S is equal to C. Is that okay? Have I clarified this? Measure of distance between W and Chi-S. Why is W hat S a measure of distance between W and Chi-S? Right. So this we will always
Yes.
remember, that we can always capture the distance between a function and Chi-S using its Fourier coefficients. And now another question, since we have understood this, if how many different S's or distinct S's can be there such that W hat S is more than half?
Just one.
Why?
Because the distance is less than n by 4, right? So there can only be one CS such that the distance of W and CS is less than n by 4.
Okay.
So there can be at most one. So there can be
Very
only one CS where the corresponding coefficient is greater than equal to 1.
Sounds good. Yes. So why? Because this basically means that W hat S greater than half means W minus CS is less than n by 4. Suppose there were two CSs. Let's say W minus CS is less than n by 4 and W minus CT is less than n by 4. Okay, if there were two code words which were distance less than n by 4 away, then what can I say about the distance between CS and CT?
Less than n by 2.
Right, which is a contradiction. This is again what we know as triangle inequality. Right, because we know that the distance between CS and CT is exactly equal to n. Right, so we know that there is at most one W hat S, which is more than half. The way to recover your code word is take your W, do the Fourier transform, and then output the maximum W hat S. That is the decoding. Output S for which, or output S or CS, doesn't matter, it's the same thing, for which W at S is maximum. This is your decode. Sounds good. Let's generalize this to a slightly different problem, which we call list decoding. This is another question which someone has already asked. What if number of errors are more than n? Right? Let me ask a more trivial question. The answer would be simpler, the task would be harder. What if number of errors are more than n by 2?
I mean, it will go outside the code because
Yeah.
distance between.
Basically no hope, right? If more than half the bits can get corrected, then we can get confused between any two codes. Right? What I mean to say is take any two code words C1 and C2, take a W. I can always pick a W which has errors more than n by 2, which is actually distance less n by 2 from both C1 and C2. When I receive a code word W, there can be any code word can match up to that in some sense. I can get confused between any two code words. Right? But let's look at a slightly different question. What if errors are more than n by 2? Clearly, we can't uniquely decode the code. Can we simplify our new task? Can we say that there is a small number of possible code words? This is called list decoding. Instead of decoding completely, I will give a list of code words which are possible.
Can you just quickly repeat the argument why you said no hope for the case of greater than n by 2?
Actually, okay, yeah, I should probably say.
I mean, it's really intuitive, but can you just?
Okay, well, you see for capital N, right? Like N is the length.
Capital N.
Yeah.
Yeah.
Yeah, what I'm saying for n by 2 is that if you pick any two code words C1 and C2, you can come up with a word which is at a Hamming distance of at most n by 2 from both the places. There exists W such that W minus C1 and W minus C2 both are less than n by 2.
Okay.
So you can get confused between any two code words. That's the point. I shouldn't say
Okay,
no
okay.
hope, but you can get confused between, okay, sorry. Probably no hope is a stronger sentence.
So it is again similar to the list decoding, right? If then C1, C2 will belong to that list.
But in this case, you will see that the list will be really, really, really big.
Okay.
So, for example, okay, so if number of errors are more than n by 2 for Hadamard code, can you come up with a code word whose, can you come up with a code word? Yes. Let me think about that for a while, but let's worry about errors less than n by 2 now. But the list could be pretty big. Yeah, okay. So can you come up with a code word such that if the number of errors are n by 2, then every code word will be in the list?
Alternating 1 and -1.
No, actually, you pick any code word itself, right? Any two code words are n by 2 distances, right? So if your W is equal to some CS, then every code word is at a distance n by 2 away. That means if
Yeah.
I want to list decode it, every code will be there in the list. Make sense?
Yes, sir.
Right? So a number of errors more than n by 2, there is no hope. But what if number of errors are n by 2, 1 minus epsilon? If we know that number of errors are less than n by 2, 1 minus epsilon, then how many code words can be close to a W? So how many code words can be there such that W minus CS is less than n by 2, 1 minus epsilon? How will you go about it?
By Fourier coefficients again.
Right, very good. So what does this mean?
So W hat is
You have a pen and paper, do the calculations.
n into epsilon.
No. How can you say n to epsilon? WS
Divided
cannot be.
divided by 2 to the power. Sorry, then epsilon. Yeah, W hat is greater than epsilon.
Do people agree? How many people agree with this? Raise your hands. Okay, and yeah, all of you are wrong. Do the calculations again. If the distance is less than n by 2 times 1 minus epsilon, then what can I say about W hat s? Or you are probably right. No, wait. Okay, let me do the calculation.
W hat s is less than equal to epsilon.
No. You are no. You were right. W hat s is okay. I was thinking of n times half minus epsilon. Actually, sorry. Sorry.
Greater than
Yeah.
equal to epsilon.
So so if you want to take n by 2 times 1 minus epsilon, then W hat s is more than epsilon. Because again, at n by 2 plus 1 plus epsilon places, the values will agree. And at most, this many places, the value will disagree. And then I will normalize to get W hat s. This is more than epsilon. Right? Okay. And now, once we know that W hat s has to be more than epsilon, how many s's can be there? Can we give a bound? Again, this calculation of W hat s more than E, all of you should be able to. What I mean
1 by epsilon square.
is this.
That's one trivial bound.
Yes, that's the bound which is good enough for us. The answer is 1 by epsilon. Why? Why did we get 1 by epsilon square except Udit? Can anyone answer? What is the magic word here?
Parseval identity.
Exactly. Parseval's. I know that summation W hat s square is equal to 1. If each of these coefficients are contributing epsilon square, there can be at most 1 by epsilon square. That means I have at most 1 by epsilon square code words in the list. Why is this important? This does not depend upon n. That's the thing which you should marvel. Think about it this way. If I said that the number of errors should be less than n by 2 times 1 minus 1 by 10, right? So this is going very, very close to n by 2. Even if my number of errors were as much as n by 2 times 1 minus 1 by n, which is, how much is this? This is 9n by 20 or something, right? Then how many code words will be there in the list?
At most 100.
At most, right? So even when the number of errors are allowed to be very, very close to n by 2, still I have only constant many code words in my list. And they can be efficiently found. This is, I think, Goldreich Handler. But anyway, this is outside the scope of the course. I wouldn't go. But this finishes my time. Let me just say once more, Hadamard codes, great distance, and uniform distance between any two code words. Great for list decode. And all these properties we could prove using the Fourier expansion. that finishes the class from my side.